Okay, in this question we're going to show you how to execute synthetic division. It's a way of dividing polynomials, and it follows very much the same process, except we're going to just enhance the process a little bit by making it always doing an addition. Alright, so in this case here we have a degree 5 polynomial. And on the bottom we have a degree 2 polynomial. Alright, now notice in this case we have x to the 5, a 3x to the 4, a 2x cubed, a 2x squared, a 3x and a 1. Notice that all of the powers of x or exponents of x are represented here. If, for example, I didn't have an x cubed, then what I'd do is put a 0x cubed in there. Okay, this is one of the most common errors, is to just ignore that. Alright, so we set it up like this. I draw it like this. There's a number of ways you can draw it, but I draw it like this. Alright, I start with putting my coefficients. So this is 1x to the 5, 3x to the 4, 2x cubed, 2x squared, a 3x and a 1. Alright, now notice that if I had had 0, for example, there I didn't have an x squared here, then I'd put a 0 here to fill the space. Right, all place positions must be represented. Now the next thing is we want to find what we're dividing by, and it should be in the form x take k. We're going to keep this all as an addition, that's why we do it this way. Notice we have an x plus 2, which of course we can write as x subtract negative 2, which gives us x plus 2. So in this case here, k is equal to negative 2. So put a negative 2 here. Right, so the first step is bring down the first coefficient 1. Negative 2 by 1 is negative 2. Add. 3 plus negative 2 is 1. Negative 2 by 1 is negative 2. Notice I have 2 plus negative 2 is 0. We have negative 2 by 0 is 0. 2 plus 0 is 2. Right, negative 2 by 2 is negative 4. 3 plus negative 4 is negative 1. Negative 2 by negative 1 is 2. And we add 2 and 1 is 3. Now this last one represents the remainder, so I'm going to separate it out because this is the remainder. Alright, so, and that will of course be divided by what we're actually dividing the whole thing by, which is x plus 2. So in other words, this division, alright, the result of it is in fact, let's write it out here, 2x cubed plus 2x squared plus 3x plus 1. And when we've divided this by x plus 2, we end up with, now notice what happens here, we've got x divided by x to the 5, so it's reducing each one of these exponents. So we'll have an x, 1x to the 4, notice that. We have a 1x cubed. Now we're at the answer stage. Because this is 0, this would be 0x squared, so we don't have to worry about it since we're at the answer stage. Then we have plus 2x, subtract 1, plus a remainder of 3, which would be 3 over x plus 2, just like we do with numbers. When we have a remainder, it's whatever that number is over what we're divided by. Now alternative, and this is one of the reasons why we actually do synthetic division, is we can write this top polynomial in a reduced form, or a kind of factored form if you like. So here we have our top polynomial. Now if I multiply both sides, we're going to multiply both sides by x plus 2. Right, notice what happens here. This will cancel out here, and this will cancel this one out here. So I'll have an x plus 2 times by this polynomial that we ended up with, and of course the x plus 2 will cancel out here, and that'll leave me a 3 there. Right, and so in other words, we sort of have a factored form here that if I do x plus 2 times x to the 4 plus x cubed plus 2x minus 1, and then add 3, we'll actually end up with this top polynomial. Alright, and sometimes we want to write it like this, so we can start getting a factored form, and of course if we had a remainder of 0, then this would of course allow us to actually factor this top polynomial. So synthetic division has a number of uses in this regard, and that's how we actually execute it.